Let's get it. Let's get it. All right, washer method. Same sort of concept as the disk method, except now we're going to create a washer instead of a disk. Ever seen a washer? You know what I mean? Like a donut used to put on like screws and stuff. You've seen a washer before, haven't you? You know, it's all filled in like this. It's got a hole in the middle. Yeah, we're going to create some of those. So we're going to have a function on top of another function, and that's going to be the game. So let's see some pictures. All right, let's say we have a function on top of another function, and then it creates some region from A to B. Now, if you revolve it about the axis, hey, it produces a solid with a hole. It just creates this washer. And we don't really care about the whole volume part of it. We're just thinking we just have to find the freaking area. And it's the same gosh darn area. It's the same area. Because we're going to take the area of our bottom function, that g of x, and we're going to revolve that about the axis. Sorry, my drawings suck. We revolve them about the axis, so we're going to subtract out that area, or that volume. And then we have our other volume, the bigger one, and we're going to take that part, and we're going to subtract out the smaller part. We'll subtract out this little piece in the center. So, all right, I should probably stop drawing. I already have pictures set up. And they're much better than anything that I can draw. So that's the cross section. The area is this little washer, which is just higher, and I like the way they write this. R sub 0, outer, the top. R sub I, inner, the inner function. So we have to take the area of the outer function and subtract out the area of the inner function. And there's our cross section. It's just pi times the outer function squared minus the inner function squared. Same game as what we were doing before. It's almost like that area between curves. Almost like the area between curves. Almost, but not quite. So here is our here's our definition. The washer method about the x-axis. Let's f and g. They got to be continuous functions. And we just want one function to be bigger than or at least equal to the smaller function. All right? And then we want to keep that stuff positive or 0 at least. On a closed interval. So let's let R be the region bounded by y equals f of x, y equals g of x, and the lines x equals a and x equals b. Then when we revolve that region R about the x-axis, the volume will result in the integral from a to b of pi times the quantity of the outer radius squared minus the inner radius squared. Let's try a problem. This is a classic. I think I had this on a test. So we're going to do volumes by the washer method. So the region R is bounded by the graphs of f of x is equal to the square root of x, and g of x is equal to x squared. Between 0 and 1, what is the volume of the solid that results in R when R is revolved about the x-axis? Okay. What's the top function? What's the bottom function? I remember Calc 2 is where I finally got this. In between 0 and 1, the square root function is actually bigger than the x squared function. So I'm going to write our f of x here. This is the square root function to 1. Now, of course, it keeps going in. I've made it a little bit more ridiculous, but there's your f of x is equal to the square root of x. And then we have some g of x, and that's going to be the parabola that comes up like that. There's our g of x, and they connect, of course. All right. Square root of 1 is 1, 1 squared is 1, 0 squared is 1, square root of 0 is 0. So we're going to have some region right here. That's our region R that we're going to take, and we're going to revolve it about the x-axis. So it creates a little, there's our little delta x, And then once we take this and we revolve it about the axis, we're going to get some sort of strange little picture. So I just kind of do one of these. Sorry, my pictures suck. Inside of here. So we're going to be subtracting something out. Cool. Neat. Fascinating. Fascinating. But what we needed to know, I know I keep trying to show pictures and get you to go, but this is the way it breaks down. You just got to know the top function. You got to know the bottom function. So when we set this thing up, we want our area function to be pi times our top function squared. That's the square root of x squared minus our bottom function squared. And I know I keep not going to your formula. I just keep thinking area. Just find the gosh darn area. And that's the region in green. So then we can say that our volume is going to be the integral from 0 to 1 of pi times our square root of x squared. That's just x. Minus x squared squared. That's x to the 4th. dx. Now we solve our integral. So it's all about the setup. Shoot, you might have a problem on your exam where I don't even ask you to solve the integral. I just ask you to set it up. Because at this point in time, you can't solve that integral. We got some serious effing issues, right? I'm not saying like we do it 100% of the time and never make a mistake, but if you can't solve that integral at this point, what the hell are we doing here? So there may be some on your exam where I'm like, just set the integral up. Just set it up. So that's going to be our big trick, and that's what we want to practice. So, but I'm going to finish this one off, and we get what? X squared over 2 minus x to the 5th over 5. Evaluated from, oh, I love zeros. Zeros are the best. So it's pi times 1 squared over 2, 1 to the 5th over 2, minus absolutely fricking nothing, because zeros are the best. Oh, that's supposed to be a 5. Supposed to be a 5. Come on, man. Why didn't you yell at me? Oh, yeah. You're not here with me. So we have 1 half minus 1/5. So we need to get that common denominator of 10, which means we need to multiply that by 5, this one by 2. So what do we get? 3 pi over 10. 3 pi over 10. That's what we got. So this is the type of problem. Shoot. Set something like this up. That would be a great sort of test problem. I don't need to go too nuts, but there's one that I would actually have you solve. Yeah, well, that's not so bad. Not so bad. So what do you think about this stuff? I don't think it's so bad. Square the top function, square the bottom function, subtract them from each other, multiply by pi, take the gosh darn integral. But you got to know what's up top and what's down below. All right, so then on our next one, we're going to deal with our y-axis, and then I'm going to leave you the heck alone on this. Maybe I'll do a big old problem. Maybe we'll do 2 more. I don't know. I'm just looking at your text. It's got some good examples. I figure give you more examples than you need, and that's probably a better thing. All right. See you in the next.